One way to characterize surfactants is by their shape. And we can see that we can imagine several different surfactants with several different shapes. So let's take a simple surfactant that's just a polar head group with one nonpolar chain. So it might be something like sodium dodecyl sulfate, where we have a polar sulfate group and then a hydrocarbon chain of 12 carbons. We can see that has sort of an ice cream cone shape. If we had a surfactant like a phospholipid, the molecules that make up cell membranes, we can see that there's two alkyl chains and then one polar head group. And we can imagine that that is more of a cylindrical shape. And of course, if we had something like a triglycerol molecule, a triacylglycerol molecule that's a fat or an oil, has three hydrocarbon chains and one very small head group. And so we can see that looks sort of like, I don't know, maybe like the command module from the Apollo program or something like that. So obviously very different shapes. And this is going to play out in how these molecules aggregate together and what sorts of aggregates they form. So it would be useful to come up with a numerical parameter to quantify molecular shape. And the number we're going to come up with is surfactant number. And this is also sometimes called the critical packing parameter because it affects how these molecules pack together. We're going to call it the surfactant number, and we're going to use N sub S for surfactant number. We're going to define surfactant number as a function of the volume of the hydrocarbon portion of the molecule over the length of the hydrocarbon portion of the molecule and the area of the head group. Let's define all these parameters. So let's take a prototypical surfactant molecule and imagine that we have a spherical head group, and we're going to slice this spherical head group across like that. We know the cross section of a sphere is going to be a circle, and we're going to say the area of that circle is A naught. That's how we're defining A naught. The length of this hydrocarbon chain is just L sub hydrocarbon. And we can imagine that the volume should have a name. We'll call that the volume of the hydrocarbon chain. And the hydrophobe on this surfactant could be something else besides a pure hydrocarbon, but we're just going to use the terminology HC for hydrocarbon. Okay, so we can see this is definitely going to be a good parameter for the shape of the molecule because the ratio of the volume divided by the length times this cross-sectional area is going to be different for every shape of molecule. Let's look at surfactant numbers for several different shapes of surfactant. So if we return to the three shapes of surfactants we mentioned earlier, we can see that in the case of an ice cream cone shaped surfactant molecule, if we divide the volume by the cross-sectional area and the length, what are we doing? Well, the length and this cross-sectional area, if we multiply them together, they give you the projected volume beneath the head group. And here the volume of the hydrocarbon is actually less than the sort of volume underneath the head group. And so the surfactant number is less than 1 because we've got the volume, the actual volume of the surfactant molecule divided by the projected volume. On the other hand, if we have a cylindrical shape, the projected volume is exactly the same as the actual volume, and so the surfactant number is equal to 1. And if we have this inverse cone shape, the projected volume underneath the head group is less than the actual volume, and so the surfactant number, since it's the actual volume over projected, is actually greater than 1. Okay, we can think about what would happen if we packed these types of molecules together. We can see if we packed a bunch of ice cream cones together, we expect that the surface would begin to curve, that this would form some sort of curved shape. On the other hand, if we packed cylinders, like Coke cans together, we expect that they would form a flat layer. And if we pack together these, they would form a curvature, but it would be inverse to the curvature that we saw with the ice cream cone shaped molecules. So we expect that there's going to be a shape associated with any particular surfactant number. So in this example, we're going to calculate the ideal surfactant number for a spherical micelle. So first, let's draw a spherical micelle. And we'll just do a sort of cartoon of this. And we know that the hydrocarbon tails in the center of a surfactant micelle are going to be in some sort of liquid-like state. So we'll draw them as being disorganized. And we right away should try to come up with a qualitative answer. Should the surfactant number be less than 1, greater than 1, or equal to 1? And we can see if we packed ice cream cones together, we would get the kind of curvature that we're looking for. So we can see that having head groups bigger than the underlying hydrocarbon gives us the kind of curvature that we see in a micelle. So we know N sub S has to be less than 1, but how much less than 1? Well, we could come up with a couple of answers here. If we just imagine calculating the volume and the surface area of one of these micelles. So first we're going to define another variable. We're going to call N sub naught be the aggregation number. And that's just the number of molecules in a micelle, or any kind of aggregate. Okay, so once we have this, we can see that we can look at the volume of the molecule and the surface area of the molecule in terms of N naught. So let's look at the sphere's area first. So the area of the entire sphere. We can say that's going to be equal to the number of molecules in the sphere times the cross-sectional area of each head group. So if you imagine each head group is occupying a certain amount of area, if we multiply the number of molecules, certainly we have the area of our sphere. We could also calculate the area of the sphere using basic geometry. We know the area of a sphere is 4 times pi times the radius squared. What's the radius, or at least the approximate radius of the sphere? If we go back, we can see that we can't make the micelle longer than any individual chain. If we did, there'd be an empty spot in the center of the micelle. And of course, nature abhors a vacuum, so we can't have empty space in the center of our micelle. So the radius is limited by the length of the hydrocarbon chain. So 4 pi r squared, or 4 pi l squared. That's the area. And let's call this equation 1. If we look at the volume of the sphere, we can say that's the number of molecules times the volume of the hydrocarbon. So we're looking just at the volume of the hydrocarbon portion of the sphere, but of course that's the vast majority of the sphere. But once again, we can come up with a geometrical volume for the sphere, and that's 4/3 pi r cubed. And once again, we're going to use the length of the hydrocarbon chain as our radius. So we've got two equations. Where our goal is to find an expression for the surfactant number. So going back to surfactant number, we see that's this ratio here. So we want volume divided by length and area. So we can get a good start at that if we simply divide equation 2 by equation 1. So we're going to divide equation 2 by equation 1. So on the left-hand side, we have volume of hydrocarbon times m sub naught divided by N naught and A naught. And on the right-hand side, we've got 4/3 pi L hydrocarbon cubed. And on the bottom, we have 4 pi L hydrocarbon squared. Now we can start canceling things. We can cancel N naught. We can cancel pi. We can cancel 4. And we can cancel all but one factor of length of hydrocarbon. So if we look what we have on the right-hand side, we now have the length of a hydrocarbon. We can move this 3 to the bottom over here. And if we simply divide both sides by the length of hydrocarbon, what do we have? We have the volume of hydrocarbon is equal to the length of hydrocarbon times A naught. And on the right-hand side, we have 1/3. So what's this? This is just the surfactant number. So we finished the problem. The ideal surfactant number for spheres is equal to 1/3. And remember, at the very start of the problem, we said we knew it had to be something less than 1. So this fits with our intuitive answer of the problem. You should probably repeat this derivation for other geometries and make sure that you're able to calculate what an ideal surfactant number would be for other types of aggregates.